This video is about the dimension of a vector space and the rank of a matrix. We have 4 objectives. We are going to define dimension. We are going to prove some theorems about bases and dimension. We're going to define rank. And finally, we're going to revisit the invertible matrix theorem. We'll start with a theorem. If a basis for a vector space V has exactly n vectors in it, then any set of more than n vectors in V is linearly dependent. The proof of this theorem in the book is pretty long and, quite frankly, a little bit tedious. It's a great example of the use of summation notation. So they prove it twice, once without summation notation, which is sigma notation, and once with it, and show how it's a more compact, more efficient proof to use the sigma notation, though it may be a little bit more difficult to follow. In any case, I don't do either of those methods here. The proof here in these notes involves coordinate vectors, this rho sub b of C1, and the concept of isomorphism, which we'll learn later in the course. So once we understand those concepts, you could come back and this proof would make a lot more sense. For now, don't worry about this proof. We'll just consider the result of the theorem, and you can look at the proof in the book. Next, we have a theorem that says if a basis for a vector space V has exactly n vectors in it, every basis for V has exactly n vectors in it. The word exactly here and here is very important. If you have $5 in your pocket and your friend asks if you have $1, it's true, you have $1. You have more than $1, but you have $1. You don't have exactly $1, but you do have $1. If, on the other hand, your friend said, do you have exactly $1 and you had $5, well then, no. The answer would be, no, I don't. So we don't often use this word exactly in everyday English, but in math, it has an important and specific meaning. So this theorem is saying, if I have a basis with n vectors, no more, no less, then every basis for V has to have the same number, exactly n vectors in it. And the proof of the theorem uses the theorem above, which says if a basis has exactly n vectors in it, well, the first phrase then is the same. Any set of more than n vectors is linearly dependent. So we simply apply that theorem twice. We assume that there are 2 bases, say B1 and B2, that are both bases for some vector space V. And let's say that B1 has n vectors in it and B2 has m vectors in it. Well, by theorem 1.1, m has to be less than or equal to n, because if it were greater than n, that would mean B2 is linearly dependent. But since it's a basis, we know that it is linearly dependent. Likewise, n has to be less than or equal to m, because B2 is a basis. And if B1 has more vectors in it than B2, by theorem 1.1, it would be a linearly dependent set, but we know it's not because it's a basis. So if we combine these 2 inequalities, m has to be less than or equal to n, and n has to be less than or equal to m, well, the only possibility then is that they're equal. M is equal to n, and therefore every basis has the same number of vectors in it. Okay, now we can define dimension. We say the dimension of a vector space is the number of vectors in any basis for V. So the previous theorem is important because it tells us that that number is a constant. If it were not a constant, in other words, if some bases had 5 vectors and others had 3 and others had 14, then we couldn't say that the dimension is the number of vectors in some basis or any basis, because which one would we use? But since every basis has the same number of vectors, we're just giving that number a name, and we're calling it the dimension of the vector space. It turns out that V is finite dimensional if the basis is a finite set. Remember, the definition of finite dimensional says that a basis is finite dimensional if it has a finite spanning set. Well, a basis is a spanning set, so a finite basis means the vector space is finite dimensional, and otherwise it's infinite dimensional. We saw earlier that the empty set is a basis for the 0 vector space, and the empty set has no vectors in it. So by our definition of dimension, the dimension of the 0 vector space is the number of vectors, namely 0, in the basis. All right, we have another theorem that says, let H be a subspace of a finite dimensional vector space V, then any linearly independent set in H can be expanded to be a basis for H if it's not already. Also, H is finite dimensional, and the dimension of H has to be less than or equal to the dimension of V. There are 2 things that we have to show here in this proof. First of all, we have to show that any linearly independent set in H can be expanded to be a basis for H if it's not already. And then secondly, we have to show that the dimension of H is less than or equal to the dimension of V. In other words, the dimension of H cannot be bigger than the dimension of V. The way to show the first part is to consider cases. So if I have a linearly independent set in H that is also a spanning set, then it's already a basis. If it's not a spanning set, then we can expand it by adding vectors to it. So we say, let's take some set B, a linearly independent set B, that doesn't span H. Well, that means that there are vectors in H that are not in the span of B, by the definition of B not being a spanning set. So let's find one of those and add it to B, and we'll call the new set, say, B prime. So now W is in B prime, so of course W is also in the span of B prime. And now maybe B prime is a spanning set for H. If it is, it's a basis. If it's not, find a vector in H that's not in the span of B prime, call it, say, Z. So Z is in H, but it's not in the span of B prime. Well, add Z to B prime, and now we get B double prime. If B double prime is a spanning set, it's a basis because it's still linearly independent, because by definition, it's not in the span of B prime. Therefore, Z cannot be written as a linear combination of the vectors in B prime. And we can continue this process as many times as we need to until eventually we get a linearly independent set that is a basis. Our next theorem says if V is an n-dimensional vector space where n is greater than or equal to 1, and that just excludes the 0 vector space, so the dimension can't be 0. Any set of exactly n linearly independent vectors in V is also a basis for V. Also, any set of exactly n vectors that spans V is a basis for V. I'll skip the proof for now. You should read through it to make sure you can follow that. But I want to focus on what this is saying. It's saying two important things. It's saying if I know the dimension, n, of a vector space, then any set of exactly n linearly independent vectors is a basis. I don't have to check to see that it's a spanning set. Likewise, any set of exactly n vectors that spans V, so a spanning set with n vectors, is a basis. So we can summarize that over here. We now have three separate conditions for determining if a set is a basis for an n-dimensional vector space. So by definition, if the set is a linearly independent spanning set, then it's a basis. But if I know the dimension of the space, if it's an n-dimensional space, then all I need to figure out is if it's linearly independent or if it's a spanning set. If I know how many vectors are in the set, if it's got n vectors and it's an n-dimensional vector space and it's a linearly independent set, then it's a basis. So if I have a 5-dimensional vector space, and if I have a set with 5 vectors in it that's linearly independent, well, then it's a basis. If I have a set with 4 vectors or 17 vectors, anything other than 5, well, even if it's a linearly independent set, it's not a basis. Likewise, if I have a set of 5 vectors that's a spanning set, it's automatically a basis. I don't have to check to see if it's linearly independent. This is a really convenient theorem because we often do know the dimension of a vector space, and when we're trying to find a basis for that space, we really only have to make sure we have n vectors and then either make sure that the set is linearly independent or that it's a spanning set. We don't have to do both. Okay, the last theorem in this section says if A is an m by n matrix, then the dimension of the null space of A is equal to the number of free variables in the equation AX equals 0, and the dimension of the column space of A is equal to the number of pivot columns in A. The proof is very straightforward. We have a theorem that says that the pivot columns of A form a basis for the column space of A. Well, the number of vectors in the basis is the dimension. So the number of pivot columns is equal to the dimension of the column space. Also, since there will be one free variable in this equation for each non-pivot column of A, and each free variable corresponds to a basis vector for the null space, then the dimension of the null space is the number of basis vectors, which is equal to the number of free variables, which proves the first part. Okay, so now we come to some more definitions. We define the rank of an m by n matrix A, written R of A like this, to be the dimension of the column space. So we're talking about the dimension of the column space, and down here the dimension of the null space. That's kind of a mouthful, and there's a lot of symbols we have to write there. So we're just giving a name to the dimension of the column space. We call it the rank. The dimension of the null space we call the nullity, and we write it n of A. So R of A is the rank, it's the dimension of the column space. N of A is the nullity, it's the dimension of the null space. We use those definitions immediately now in the rank theorem, one of the most important theorems in the course. If A is an m by n matrix, then the rank of A is equal to the dimension of the row space, and the rank plus the nullity is equal to n, which is the number of columns in the matrix. The proof, again, is very straightforward. The dimension of the row space is equal to the dimension of the column space because they're both equal to the number of pivots as described down here. And the second part is just a combination of these two definitions, really. The rank is the number of pivot columns. The nullity is the number of non-pivot columns. So the number of pivot columns plus the number of non-pivot columns is equal to the total number of columns, which we can see here. And just to emphasize where this comes from, remember the dimension of the column space is just the number of pivot columns. The dimension of the null space is the number of non-pivot columns by the theorem we saw in the previous section. So this equation summarizes the rank theorem. The rank plus the nullity equals the total number of columns. And we can use this in obvious ways. If I'm given a matrix, I can just observe the number of columns. If I know the rank, then obviously I can figure out the nullity, and vice versa. If I know the nullity, I can obviously figure out the rank. So the rank theorem basically says, if you know either the rank or the nullity, you get the other one for free. All right, let's look at an example now. Given the matrix A below, find bases for the column space of A, the row space of A, and the null space of A. We actually did this example in the column vectors chapter, and instead of bases, we were asked to find linearly independent spanning sets for the column space, the row space, and the null space. Well, now we just have a special word for linearly independent spanning sets. We call those bases. So we're going to do the same example, and we're going to use the same technique that we did in the previous chapter. So really, you already know how to do this. We're just changing the word. So to find a basis for the column space, we row reduce A and then take the pivot columns. So here's A. Here's the row reduced form of A. And we can see the pivot columns here in columns 1, 3, and 5. So that means columns 1, 3, and 5 of the original matrix A form a basis, a linearly independent spanning set for the column space of A. Here's our basis. Remember, we have to be careful to choose the column vectors of the matrix A and not the row-reduced form of A. If we chose these three vectors, notice they all have a 0 in the last entry. So the span of the set containing those three vectors would not be the same as the span as the set containing these three vectors in particular. Here is a non-zero entry in the fourth entry of a vector. So I could get vectors that have a non-zero entry in the fourth entry as linear combinations of these vectors, but not as linear combinations of this one, and this one, because they all have a 0 down here. So the span of this set is not equal to the span of the set containing these three column vectors. So that's just something to be careful about when you're using that theorem. The theorem tells us that the pivot columns of the original matrix, 1, 3, and 5, form a basis for the column space, not the pivot columns of the row-reduced form of the matrix. Then, to find a basis for the row space of A, we simply look at the non-zero rows of the row-reduced form of A, and we write those as column vectors. So 1, 3, 0, minus 3, 0 is written as a column vector here. This row is written as a column vector. This row is written as a column vector. This row is all zeros, so we don't include it. And our previous theorem tells us that this set is a basis for the row space of A. And then to find a basis for the null space of A, we solve the equation AX equals 0. So the solution set to this equation is the null space, and we can get a basis for the null space by taking the set of linearly independent vectors corresponding to the free variables in this system. So we can solve AX equals 0 by row reducing the coefficient matrix, which we already did. So that's back up here. Here's A. We row reduced it. So now we write down the system corresponding to the row reduced form of the coefficient matrix. So 1x1 plus 3x2 plus 0x3 minus 3x4 plus 0x5 equals 0. So that's what we have here. And then we have an equation for this row, here, and here. Okay, and then as usual, we solve this system for the basic variables or the dependent variables in terms of the free variables. So x2 and x4 are free because there are no pivots in those columns. x1, 3, and 5 are the pivot columns, so we solve for those in terms of the free variables. Notice that this equation says x5 is equal to 0, so it doesn't depend on x2 or x4. So even though it's a dependent variable, it's actually just always equal to 0. So there's no x2 or x4 in this equation like there is up here for these other dependent variables, and that's totally fine. So we can write the parametric solution. We write x as a vector in C5. x1 is this expression, x2 is free, x3 is equal to x4, x4 is free, x5 is always 0, and then we can factor an x2 out of each term here to get x2 times this vector, and then factor an x4 out to get x4 times this one. So these two vectors form a basis for the null space of A. The null space of A itself is the span of that set. This is another important thing to notice. It may seem like a small difference, but it's very important. The basis has only two vectors in it. The span of the basis is the entire space. It is the null space, and there are infinitely many vectors in the span of this set that contains only two vectors. So we were asked to find a basis, and so this is the answer. This is the basis for the null space. This is not the basis for the null space. If this were on a test or a quiz, this would be a wrong answer, because this is the entire null space. We just want a basis for the null space, and this is the basis. And now we can notice that this example demonstrates the rank theorem. So the rank theorem says that the rank of the matrix, which is equal to the dimension of the column space, which is also equal to the dimension of the row space, is the number of pivots. And the number of pivot columns we had was 3. And the nullity is equal to the dimension of the null space, which in this case was 2. Notice there are 2 vectors in the basis for the null space. So the dimension of the null space is 2. And there are 5 columns, and what do you know? 3 plus 2 is 5. The rank plus the nullity is equal to the number of columns, which we can see here. And the rank theorem says that this will always happen. All right, here's another theorem. If we have an m by n matrix A, the rank of A is equal to the rank of A transpose. And that's a very simple proof because the matrix A has the same number of pivots as A transpose. Another way to think of it is the column space of A is equal to the row space of A transpose and vice versa. So here's the details of that theorem. Okay, finally, we're going to look at the invertible matrix theorem again and see how it's growing. So we've got up to S statements in it now. And remember that these are all logically equivalent statements. And that means that they're either all true or all false at the same time. So this is a very powerful theorem because if I can figure out that any one of these is true, I know they're all true. And if I can figure out that any one of them is false, well, then I know that they're all false. So if A is an n by n matrix, up here, the column space of A is equal to Cn. The columns of A form a basis for Cn. The dimension of the column space is equal to n. The null space is equal to the set containing the 0 vector. The nullity of A is 0, and the rank of A is n. These statements, n through s, are just a direct result of our new definition of dimension and rank, and then applying these statements up here. For example, statement O here that the column space is equal to Cn. Well, H says the columns of A span Cn, and the column space is nothing more than the span of the columns of A. So O is just another way to say A. The dimension of the column space is equal to n. Well, Cn is n-dimensional, so P is really just another way to say O. The rank of A is equal to n. Well, the rank of A is defined to be the dimension of the column space, so Q is just another way to say P, etc., etc. And that's what logical equivalence means here. Really, all these statements are just different ways to say the same thing. The usefulness of this is that sometimes it's a lot easier to figure out that one of these statements is true or false than some of the others. But if I can figure out that a single one of these is either true or false, I know that all the others have the same truth value, we would say. So, for example, if I can figure out that the rank of a matrix is not equal to n, if I have, say, a 7 by 7 matrix, and I can figure out that the rank is not equal to 7, let's say the rank is equal to 6, well, then I know this statement Q is false, and that means all of these statements are false. The matrix is not invertible, it does not have 7 pivots, this equation does not have only the trivial solution, in other words, it has non-trivial solutions, etc., etc. So the invertible matrix theorem is one of the most powerful theorems in the course because it's got all these logically equivalent statements in it. All right, that finishes our video on dimension and rank. We defined dimension, we defined rank, we proved some theorems about bases that are related to the concept of dimension, and then we looked at the invertible matrix theorem again.